So for this first one, what is my index? What grouping am I looking for to be able to pull it out? How many in a group? What's my index? 2. So my index is the number that is out here. Remember, if you don't see one, it is assumed square root. So that means in order for something to come outside of the root, it has to pair up in groups of 2. In groups of 2. And so I'm going to factor my number first. I'm going to take this 18, that's 2 times 9. And 3 times 3. I am looking for things that are in groups of 2. This 3 is in a group of 2. So that means a 3 is going to come out. This 2 does not have a group of 2. So it is going to stay inside my radical. Let's look at my variables. Remember, with variables, there's 2 ways you can do it, right? X to the 7th. And then we have y to the 9th. Now you could list out 7 x's and you could circle them around, right? But I told you another way to do that is to use division. So if I'm looking at my x's, I need groups of 2. So how do I figure out how many groups of 2 I'm going to have? Well, I will just divide by 2. That's what grouping I'm looking for. And I'm going to use remainder here. I'm going to use remainder. So 7 divided by 2 is what? How many times does 2 go into 7? 3 times with a remainder of 1. This tells you how many come out. This tells you how many stays in. So 3 is how many groups you would end up with. You would end up with 3 groups. So I'm going to have x cubed comes out. And this tells me what stays in. 1x stays in. X to the first power stays in. All right, y to the 9th. Same thing here. You could write out 9 y's if you want to and circle them in groups of 2, but the easier method here when you have a high exponent is just to use division. So I'm going to say 9 divided by 2. I need groups of 2. How many times does 2 go into 9? 4 times with the remainder of 1. This is how many groups you would have. So this is how many y's you would have on the outside. This is how many remain on the inside. 1. So that would be my answer. This would be my answer here. Again, what is my index? It's 2. So my index again is 2. I am going to do exactly the same thing. With a fraction, your answer is just going to be a fraction. We're going to do the square root of this numerator and the square root of the denominator individually. And then we are going to have our final answer. If something stays in, put it under the root. We'll talk about actually in the next day or so how to get things out of the radical on the bottom. But right now, all you have to worry about is doing it this way. So I'm going to do the same method. I'm going to say x to the 6th. 6 divided by 2. What is 6 divided by 2? 3 with the remainder of 0, which means I have no x's that stay in. All of my x's come out. 3 groups, so x to the 3rd. No x's on the inside. I'm going to do the same thing with my y's. Y to the 6th. 6 divided by 2, again, is 3 with a remainder of 0. All of my y's come out. 3 groups of them. All right, and then we should know this square root. What is the square root of 100? It is 10. If I did not know, I could do my factor tree and every group can come out, right? But you would get 2 2s and 2 5s, right? So you would get a group of 2 and a group of 5 come out. And that is my final answer there. A lot of times people, when they get to these higher roots, then they start getting confused thinking that there has to be a radical. But if I were to just plainly ask you what this is, you would tell me 6. You would not say the square root of 6. That doesn't make sense, right? So don't forget what it means. If you have taken all your groups out and no groups remain in, your radical symbol is actually gone. You have no radical symbol at that point. My index here is 5. So I am now looking for something that groups 5 times. All right, if you do not know the 5th root of 32, you can use your factor tree. It does have a perfect root. You will see that I have 1, 2, 3, 4, 5 2s there. So I have 1 group that comes out. I do not have any 2's that stay in. I'm gonna move this a little bit. So I have a 2 here on the outside of my radical. No numbers are gonna stay in. Let's look at my variables. I have a to the 5th. I am looking for groups of 5. So 5 divided by 5 in every group is going to be 1 with the remainder of 0. How many A's are coming out? How many groups are coming out of A's? 1 group is coming out. How many A's are staying in? 0 A's are staying in. All right. And you actually don't even have to put this little index or exponent there. And then I'm going to do the same thing with my B. 15 divided by 5, what is that?
3.
With the remainder of 0. That means 3 groups come out. So B to the 3rd is out here. None of my B's stayed in. My radical sign is gone. I took everything out of the radical. So this is my final answer here. The product property of radicals is also used to multiply radicals. Couple things you need to pay attention to. In order to multiply radicals, they have to have the same index. All right? They have to have the same index. The reason this is true is we talked about writing them in exponential form. The radical index represents the denominator, right? And so when you multiply like bases, you add their exponents. The only way to add an exponent is to have a like denominator. So you could potentially rewrite this and adjust it, get a common denominator, and then do your multiplication or your addition of your exponents. But if you're just doing straight multiplication here, you cannot multiply if they do not have like index there. So same index before they can be multiplied. As long as they have the same index, you can just multiply what's inside. So you'll notice these have an n, which represents the same number for each of them. And all they did was multiply the insides. So let's look at this example. We have the square root of 2 times the square root of 6. All right. What's the index there? 2. They're both 2. So we can just multiply the insides here. We can multiply the insides. So we can say that's going to be the square root of 12. Now what you need to think about here is this in simplest form? Simplest forms means that I cannot take anything out of the root. Is that in simplest form? No, it is not. Why not? You can take out a 2. Now, I will tell you, when you have 2 and 6 square root of 12, it's going to be 2 times 2 times 3, right? So if I did my factor tree here, I would say 2 times 6, 2 times 3. You can see that the 2's will group up, that the 3 does not group up, and it's going to look like that, okay? Now let me tell you what I do, because when I make these numbers larger, so let's say I have 12 and 36. You can multiply 12 and 36, and you're going to get this ginormous number that you then have to use a factor tree for. Or you can just factor them individually at this point. And I'm going to show you what I mean by that. The only factor of 2 is 2, right? That is prime. So we are factored. You see that? The factor of 6 is going to be 2 and 3. If I am multiplying it, my answer will multiply 2, 2, and 3, right? So at this point, before I even multiply across and say, oh, it's going to be 12, and then say, oops, I can simplify that 2 square root of 3, I can actually factor them individually, right? And I can go ahead and group up any of the factors that work out for both of them. So at this point, before I even multiply across, I can see my 2's are going to group up, my 3 is not, and I can go straight to this answer. Instead of going to this answer first, factoring the 12, and then getting to this answer. Does everybody see why I would do that? Because 12 is not a big number, but you have 2 large numbers that have lots of factors, then you're going to be multiplying those 2 to then just break them down again. It's like multiplying so that you can go back and divide. Why not just divide up front if you're going to multiply anyway, right? And so that's what I'm doing up front with these. I'm just going to factor tree it first and go ahead to my most simple answer from the very beginning. And that holds true for this next one. They break it down in primes, but they don't show you why they do it that way. So if you look at example 2, why am I going to multiply 18 and 50, right? That's going to be, what, 900? So I don't want to multiply 18 and 50, get 900, and then do a factor tree for 900, even though I can do that pretty quickly in my head, right? I can go ahead and factor tree them individually. And so I already have a 2 on the outside. Everybody see that? That's just going to stay there. -2 on the outside. I already have a 5 on the outside. It stays. That's on the outside. Now I'm going to see from what I'm multiplying, can I take anything out? So I am now going to do factor trees for these. I'm going to say 2 and 9, 3 and 3. I'm going to hold off to do my grouping at this point. I'm going to do my 50, 2 and 25, 5 and 5. All right. Does anything group? My index is 2. Does anything group that can come out? Well, yeah. These 3's group, right? So that can come out. These 5 group, so that can come out. Yes. Anything else group? My 2's. It does not matter that they're in the different numbers because I'm multiplying those numbers. So this is also a group, even though they come from different numbers, because I'm about to multiply them. So they're going to group naturally. All right. So then my question is, does anything stay in? No, I have taken all my primes out. So this is going to be a perfect square when I'm all done with this. This is going to be a perfect square, which again, if you knew 900, 900 would be a perfect square. So now at this point, I can just multiply. I can multiply -2 times 5. I would actually do it this way. -2 times 5, -10, +10, and 3. What am I going to get there? 10 times 10 is 100 times 3 is 300. Don't forget your negative. My answer here is -300. Okay. And so when you're multiplying radicals, as long as they have the same index, you can go ahead and factor them individually and group all of those however your index indicates you would group them. All right. The key there is you cannot do it unless they have the same index. Good. All right. Apply the product property. It says write the radicand as a product of its primes. Simplify the root of each power. Simplify the resulting expression. Example 3 here. Example 3. Simplify these. This is the same concept. We're just throwing variables in. All right. So let me make him a little bit bigger. I am going to do exactly the same thing though. I have a 6, which is 2 and 3. I have an A. I have a B. This is n prime, right? This is n prime. I have a group. My 2's group up. So my 2 is going to come out. My 3 does not group up. So my 3 is going to stay in. All right. My A's do not group up. There is no other A to talk about. So an A is going to stay in. My B's do group up. I have a B here and a B here. That groups. It's going to come out. My C does not group with anything. My C would stay in. Works with variables too. If I had variables to a power, just to say it, I don't think they give us the example here. They give it to us later. But if you have variables to a power, you can do the division property. Just forget because you're multiplying, you would add those powers before you divided. So in this case, I have B and B. Remember, you add the powers when you're multiplying, so that's technically B squared. Well, 2 divided by 2 is 1 with the remainder of 0. That's exactly what happened here with the B's. All right, so when you're multiplying like bases, don't forget you're adding their exponents. So you can take all the variables from both sides and add them before you do your division method. What's my index here? 3. This is one you definitely would not want to multiply, right? We don't want to multiply those numbers. What goes into 225? Easily. What easily goes into 225? You can see it quickly. 5, right? 5 goes into 22 how many times? 4 with the remainder of 2, so 25 how many times? 5. What goes into 45? 5 and 9, and then 3 and 3. All right. Use your easiest. Let's look at the next one, 315. What also goes into 315? 5 and 5 goes into 31. How many times? 6. Remainder of 1 goes into 15. How many times? 3. What goes in easily goes into 63? Look, prime. So I would use 3 here, right? And 21. 3 and 7. Right? Yes. What's my index? So what grouping am I looking for here? 3s. Groupings of 3s. So we'll start with the 5. How many 5s do I have? 3. I have 1, 2, and 3. This is one group that's going to come out. What else groups? 3s. I have 1, 2, and 3. Right? So a 3 comes out. What does not group? 3 and 7. So this 3 does not have a group. This 7 does not have a group. All right. So inside the radical, I'm going to have 3 and 7. Remember, you just multiply what's left. So on the outside, I'm going to have what? 15. And on the inside, I'm going to have what? 21. Don't forget your index. What was my original index? 3. It needs to go right here. Don't forget that. That is a really easy small points off that adds up, okay? Don't forget to leave your index off. There is a difference between the square root of 21 and the cubed root of 21. That's a different number, all right? So make sure you put your index. So let's talk about this one. This is the cubed root. So I am going to, what I'm really going to do here, probably at this point when you're working, is I would likely just rewrite it with everything grouped. So I would just group the 4 and the 32 so you can break those down. Group the x squared and the x. Group the y to the 5th and the y, right? And then you have this little z. I mean, not, I wrote x, but it's a z. All right, then you have this little z here at the end. So just make sure that you've accounted for everything. I'm only saying that because we're going to combine those x's and those y's before we do our division. You can still do these individually, and I would. That's 2 and 2. This one is 2 and 16, 2 and 8, 2 and 4, 2 and 2. All right, so we're going to do that exactly the way that we would. What's my index? So what group set am I looking for? My index is 3. So I need groups of 3. So I have 1, 2, 3 there. So a 2 is going to come out. I have 1, 2, 3 here, right? Another 2 is going to come out. And then I have this lone little guy here that is going to stay in, right? That's going to stay in. So I have a 2 on the inside. Now, when I consider my variables, I need to consider exactly how many I have. All right, this is multiplication. So how many variables in total for x do I have? 3. I have 2 from the first set, 1 from the second. So this is x cubed. So when we do our division piece, we would say 3 divided by 3. That's 1 with the remainder of 0. All right, do you see where I'm combining those? So I'm going to have an x come out. No x's are going to stay in. I'm going to do the same thing with my y's. How many y's do I have? 6 y's. So I have 6 divided by 3. That's 2 with a remainder of 0. I'm going to have 2 y's come out here. None are going to stay in. I only have 1 z. Is it going to group in thirds? No. It is not. So my z is going to stay in, and my index is 3. And then I'm just going to simplify like I would. 2 times x times y squared is 4x y squared. Nothing really simplifies on the inside, so that's just going to remain 2z. Don't forget your index of 3. Don't forget your index of 3 before you do your final answer here, which is 4xy squared cubed root of 2x. is that you multiply the outsides and you multiply the insides. You do not multiply outside to inside, ever. All right? So distribution is something that some of you just grasp and some of you still are struggling with a little bit. So this works exactly the same as normal distribution. Whatever is on the outside, you are going to distribute to everything on the inside, right? If I were passing out papers and I just passed it out to the first row, that is not distribution, okay? Distribution is to every row, right? Same thing with this distribution here. Whatever's on the outside gets distributed via multiplication to everything on the inside. Now, keep in mind, indexes have to be the same, all right? If it's on the outside, it multiplies to outside. If it's on the inside, it multiplies to inside. So let's look at this first one here. All right, we're going to take this one. We're going to look at that, all right? So I am distributing a square root of 5 through, all right? Square root of 5 times the square root of 3. I'm just going to multiply the 5 and the 3. They're both on the outside. That is the square root of what? 15. Minus the square root of 5 times 2. Is 2 on the inside or the outside of a root? It is on the outside of a root. There is no root around it. So what is on the outside of my square root of 5? If I don't see something in front of it, what is it? Not the index. What number is on the outside? It's just a 1. It's almost like a coefficient on a variable, right? So this is just going to be 2 times the square root of 5.
Oh, so you can't.
You cannot multiply outside to inside. So think of this as a 1 here. All right? You can think of this as the square root of 1 for all I care. It doesn't matter. The only thing that could possibly be on the inside would be a 1, right? Square root of 1 is just 1. But when you're multiplying a whole number and a radical, they just go together. Whole number on the outside of the radical. All right? Whole number on the outside of the radical. This is my answer because you cannot subtract these. They are not like radicals. All right? If I could simplify either one of them, I would. But 15 is just 3 and 5. Nothing groups, right? 5 is already prime. Nothing comes out. So think of it as an x and a y. If I had x minus 2y, that would be my answer. I would be done, right? It's the same for radicals. If they are not alike, you are finished. You cannot combine them, all right? And so this is actually my answer. This whole thing here is my answer, all right? Let's look at the next one. We're going to do this one a little bit differently so that we can look at it a different way. All right, let's look at this guy. We are distributing this entire thing through, all right? So I'm going to write it out. I'm going to distribute this to this. I'm going to say 2 square root of 16 times the square root of 15. All right? Everybody see that? Minus. And I'm going to distribute this across to this. 2 square root of 6 times 3 square root of 10. All right? Okay? Now, if I were distributing a negative, we'd have to talk about positive negatives, but we'll worry about that later. Now, if I have this, I have 2 on the outside already. It's going to stay on the outside, right? 2. All right. Let's look at this. I'm going to factor this. 2 and 3, 3 and 5. What's my index? 2. In what numbers then do I need to group them?
3.
Yeah, the 3's group in 2's, right? So this is going to also come out, right? Everybody see that? What then is going to stay in? This 2 is going to stay in, right? This 5 is going to stay in. Everybody see that? So far, so good? Then we're going to subtract. Don't forget your subtraction sign. All right. On the outside, already, I have a 2. What else do I already have on the outside? I have a 3. We've already applied the negative with that subtraction. All right. And then I am going to do the same thing here. 2 and 3. 2 and 5. 2 and 3. 2 and 5. What comes out of this group? Yeah, so this 2 and that 2 form a group. So I have a 2 that's going to come out. All right. On the inside over here, what do I have? I have a 3 that's going to stay in, and I have a 5 that's going to stay in. Everybody see this? Now all we have to do is simplify them. All we have to do is simplify, and we are finished. Over here, 2 times 3. What's on the outside? 2 times 5. What's on the inside? Over here, I have 2 times 3 times 2. What's on the outside? 12. And then on the inside, I have 3 times 5. 15. This is my final answer right here. That's my final answer.